About 66% of the companies we spoke to said we are doing something in terms of quantum. The financial sector has really started to look at what quantum can bring to them from an optimization standpoint. The key here for the US government is the ability to draw on a vibrant domestic commercial sector to fulfill their specific needs for national security agenda requirements. China is going, in some sense, the other way.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey, Shaheen. Good to be with you again.
Excellent to be here, Doug.
Great.
We have another very, very special guest.
I would say very, very special. Bob Sorensen. He is Senior Vice President of Research at HPC industry analyst firm Hyperion Research. Bob, we're going to talk about quantum today and the state of the quantum industry. We're very glad to have you.
Well, great. Thank you very much. I appreciate the opportunity to speak again. And the fact that I'm very, very special is well appreciated.
Bob, I think you are one of the first, if not the first, repeat guest for our famous podcast.
Well, again, I'm deeply honored by that. I think that's in keeping with quantum. You know, before I was in superposition 0, now I'm in superposition 1. So that makes a certain amount of sense.
Yep, Bob, in calling you very, very special, I chose my words carefully. So anyway, as mentioned, we had you on about 18 months ago to talk about the state of the quantum market, the quantum industry. Last month at the ISC conference in Hamburg, you delivered an update, and I'm curious what your thoughts about the most significant or interesting changes, developments, evolutions in quantum ensuing period of time.
It's interesting. You know, the first off is we rolled out our market forecast in December and presented that at ISC. And the key there was stable and steady growth, which I think is a really strong aspect of the sector. Despite some of the hype you may see in the press and claims that are being made that may be considered spurious or not, we're seeing an organizational understanding of what quantum is and what it can become from the slow and steady growth perspective. And how I look at that was the idea that even say 18 months ago, companies were expecting perhaps too much about quantum, too much performance too soon from too many different companies. What I'm seeing now is a retrenching within the potential and even current end user quantum computing early adopter user base, which is, we know this is going to take time. We're not expecting 1 million qubits next week. We understand that this is a journey. We're here for the long term, and we see the benefits of preparing early. My quote of the week when I was at ISC was stolen from Vince Lombardi, which was, if you're 5 minutes early, you're really 10 minutes late. And I think that's what I've seen from the sector itself. The end users understand that this is a journey, and the final version, whatever that may be, isn't right around the corner. So there's a little more realistic expectation of what could happen. The other thing, and because it was ISC, is just a huge appreciation for what I consider to be some strong EU-based quantum computing capabilities, spurred in large part by a very comprehensive Euro HPC program that really seeks to merge quantum computing with their exascale compute program. And I think that that's really going to help energize, at least in the EU, the idea of quantum computing as a commercial capability, as something that sits aside the exascale computing capabilities. The US, in contrast to some extent, there's a little more disparity between quantum computing research, perhaps say at the government level through government policy initiatives, and what's going on in the commercial sector, which of course, rightly so, is geared towards commercialization. So to me, it's the policy aspects of this writ large, maybe having a little more impact on the sector than what I saw 18 months ago.
Yeah, you're now sizing for this year, 2023, you're sizing the quantum industry, the quantum market at 770 million, growing to over 1 billion in 2 years. I mean, that's kind of getting into significant money, leaving aside the workload hype-related discussion. There's a lot of money sloshing around in quantum. Never mind the venture investments going on.
Well, just an example, the EU announced, the Euro HPC JU announced that they would be investing 100 million euro to procure 6 different European-based quantum computers, hardware, for installation in HPC centers for access for all the members of the European HPC activity. So that's 100 million euro, we'll call it $100 million-ish, infusion in the next couple of years just because of one government procurement decision. So the growth there, and again, procurement policy, I think, is going to start to hold sway in terms of driving the sector and kind of supporting the commercialization of it. And that can only lead to increased awareness, at least from end users in the commercial sector, to say, hey, there's something going on here. So as long as we see a continued enthusiasm from a government policy support, and as long as the VCs don't decide to abandon the sector, I think we're going to maintain a certain amount of reasonable growth going forward.
Now, there's two recent pieces of news from Intel and IBM that we have on the Inside HPC site. I'm sure you're familiar with both of them. And we see that IBM had a cover story in Nature magazine, so we can assume this was peer reviewed, about work with over 100 qubit chip. Can you talk to these news announcements and your view on the significance of them?
Well, to me, the qubit count issue as an absolute number doesn't really mean too much to the average end user. It's really about how those qubits can be applied to a compelling computational problem that they're facing. To me, what's happening with, say, a company like IBM is their commitment to showing sustained progress in the sector, whether it be raw qubit counts, some of their new systems have multiple hundreds of qubits on them, or the ability to attack what I consider to be the most pernicious problem in quantum computing, which is noise management, noise suppression, dealing with the noisy environment quantum lives in. And so that was one of the more compelling issues here, is that IBM is committed to saying, here's where we were, here's where we are, and here's where we're going. And when a company can show those incremental gains, that's when you can say, I trust this roadmap. They're hitting their mark. They have a cohesive plan going forward. So really, I tend to look at the slope of a roadmap from a progress standpoint as opposed to the X values of it. And like I said, IBM has a very broad and rich way of attacking the problem. And looking at some of the noise issues is probably, I think, one of the most interesting ones going forward. So I'm perfectly happy to hear that they make progress in those areas. Now, I will say, from an end user perspective, end user, as I said, time and time again, they're interested in performance on demonstrated use cases. So while the Nature article is wonderful from a scientific perspective, I don't think any C-suite executive is going to make a decision based on a cover story in Nature. It's going to have to come from something a tad more pragmatic. So the research aspect, demonstrating capability is important, but at the same token, doing some of the other things that IBM does pretty well, such as reaching out to the end user community to help integrate their progress, their capabilities into important use cases, is, in my mind, equally as important.
Bob, as you mentioned, the market with 100 million here and 100 million there, it really soon adds up, and it has basically met the expectations that you articulated a couple of years ago when you were here. So as I like to say, for a market that isn't supposed to exist, there's a pretty substantial market that does exist. But let's talk a little bit about HPC. Is quantum going to end up being an HPC thing, just like a lot of other new technologies end up doing the same? My observation over the past many years is new technologies come in and they sort of think there's something other than HPC. They go pursue it. And then next thing you know, they find takers within the HPC world, and then they pivot into HPC. Are we going to see that in quantum computing? What
I like to say, and I was talking to some folks a couple of days ago about the so-called super chips, the Grace Hopper and the AMD MI300 series. And the conclusion I reached on those is no one is going to buy those chips for the sake of buying those chips. They're going to buy the applications that require those chips, or at least run most effectively on those chips. And I think that that's the case with quantum and the HPC environment. I see some exploration of quantum in some of the more advanced R&D facilities that use HPC, and say a Department of Energy lab would be a good example of that. But ultimately, I think if quantum is going to really move the needle in the HPC sector, it's going to be because it has use cases that matter to the HPC world, not the other way around. I don't see the HPC sector embracing these things just for the sake of the next bright, shiny object. And I would support that by looking at how GPU proliferation within the HPC world really didn't take off until the AI use case became demonstrably amazing. Driving GPUs into traditional modeling and simulation workloads was and is still a rather complex and vexing problem for a lot of HPC sites. So the value added or the use of GPUs in many cases in the HPC world was driven by the use case, not by the raw performance of the chip. And I see quantum being the same way. If it can develop the kinds of accelerating capabilities, either time to solution or in some cases, more importantly, power to solution, quantum systems can be 3 orders of magnitude less power consumptive than a classical counterpart. Even if performance is the same, that's a nice feature to have.
That's a big
If
win.
those things arise, then that's a good thing. And the HPC sector will embrace it with great enthusiasm.
Now, speaking of GPUs, we also are seeing quantum computing applications that are developed, but they don't have a place to run on. And if you can run it on a classical system, you can get rid of some of the thorny issues that aren't quite ready in a quantum computer, let's say like I/O. So you can now run them on accelerators. I like that. I think that's great. But do you think we run a risk of oversteering towards accelerators and actually end up not having real quantum computing applications because we keep optimizing it for the accelerator and it ends up not being a quantum application anymore? Do you see that as a problem, or it's all a good thing?
One of the things I like to point out is that the Navier-Stokes equations, which kind of are the fundamental equations that govern things like airflow and the aerospace industry, and everyone uses those, was developed in the 1820s, and it took an awful long time for classical computing to catch up with Navier-Stokes.
I don't think they can still do it.
Correct, but they're kicking the can down the road there.
Right.
The point there is that the classical compute world had centuries, if not millennia, to draw on interesting applications and processes. The quantum computing sector has only had the last 30 years. I think Shor's algorithm is about to turn 30 next year. So to me, what those simulators do, or the ability to actually think about algorithm development on a classical system, it helps backfill to create the kinds of thought processes that you need to develop a quantum algorithm because it's not intuitively obvious. I can probably explain to most people pretty straightforward how a binary tree works. And you can start to think about applications right off that. It's really hard to explain how Shor's algorithm really works. It's an entirely different mindset. So we have to start building an infrastructure of researchers and algorithm developers and mathematicians who are thinking about how quantum algorithms work. And if they can benefit from using classical simulators to get that process energized, then to me that can only help the sector when the hardware becomes available. No one said, let's just throw Navier-Stokes away because we can't compute with it yet. It stayed around. It had staying power because it had some mathematical underpinnings. I'd like to hope that we're developing the same kind of quantum-based thought processes and algorithmic underpinnings. And if it takes quantum simulators to do that, then I'm perfectly content with that.
So, Bob, when you've broken down the market, you've said financial, cybersecurity, and quantum R&D are the key 3 most prominent sectors of the market. Do I have that correct?
Yes, you do. But I do want to clarify that was not me pontificating. That was asking over 100 different quantum computing hardware suppliers, software suppliers, quantum computing professional service suppliers, where they saw the greatest opportunity in the next 2 to 3 years.
Yeah, I should have said this is all based on your survey research.
Correct.
Right. So if we look at, say, in the financial sector, which is listed first, so I assume it's the biggest sector of the QC market, are they just doing research? Boy, we'd love to have this thing at some point, or are they actually running workloads?
We did another study where we asked early adopters what they were up to. And this kind of goes back a little bit to the market question. We decided we wanted to hit 300 different companies to ask them about their views on their experiences in early adopter quantum computing activity. And the concern was how many companies are we going to have to talk to get 300 to come back and say, okay, here's what we're up to in quantum. The folks that fund us, that make sure that we get the right surveys, were like, we really would like to know exactly how many people we're going to need to talk to. And we set some boundaries. We needed companies that had a certain amount of financial wherewithal, that maybe had some aggressive existing computational capabilities, those kinds of things, and did reasonable R&D. And we only had to talk to about 485 companies. So about 66% of the companies we spoke to literally chose, and I don't want to say at random, but at near random, said we are doing something in terms of quantum. some form of exploration. And it could be something as simple as having a single grad student who tracks what's going on in the sector 4 hours a week and writes a summary report to the folks that write checks later on, all the way up to a small percentage that said they had things, quote, in production. I think what we're seeing here, and especially in the financial sector, is the absolute beauty of the cloud access model that allows so many different organizations to experiment, to kick the tires on, and in some cases, set up what would heretofore be considered production-like jobs because the pricing is right, the commitment and resources is good, and you don't have to make any hard decisions about hardware or software lock-in. And so I think what we're seeing in the financial sector especially is just people looking at the optimization process, understanding how to do searches, how to do risk portfolio assessments. Something happens in the market and you want to figure out, okay, this stock went under or this bond had some interesting side effects today. How can I recalculate the risk assessment of a portfolio that contains 30 or 40 instruments? Somewhat of a difficult problem to do in a classical world. So I think the financial sector has really started to look at what quantum can bring to them from an optimization standpoint. And that is enabled to some extent by how easy it is to get access to quantum compute capability on a very flexible scale. And they are always the first sector out there, in some sense, that can realize scaling, which means significant return on investment, if you will, simply because if they do something marginally better over a large customer base that involves huge sums of money, that becomes a relatively easily justifiable investment in the activity. And so that's really why I think we're seeing a lot of interest within the financial sector, just because it's something that they can do and something they can afford and something that they can justify.
So, well, one of the biggest problems of this industry, in my view, is the realness discussion. That if you're a couple of few steps removed from where the action is, it's hard to tell what's real, what's not, and what level of realness it is. So when we talk about some of these use cases, can you characterize how real they are? Are they experiments? Are they more than experiments? Are they occasional runs? Like at one end of the spectrum, you've got just kicking the tires. At the other end of the spectrum, you got it in a heavy-duty production environment. Where are we in that spectrum?
Part of it, and it's a completely acceptable practice within the classical world, which is heuristic, rules of thumb. What are some of the assumptions we can make? What are some of the variables we can throw out or confine so the job becomes something that we can do? And I think what we're seeing now, that the ones that strike me as the most practical are the ones that, as I said earlier with the D-Wave example, do you have a simple enough objective function that can get you some reasonable results, perhaps in a time frame that wouldn't be available on a classical system? And will it fit on the architectures of the day? And perhaps more importantly, does the issue of noise and the fact that I don't get a precise answer, I get a stochastic output, that's not as important to me because I'm trying to come up with basically error-tolerant solutions. So I think those are the things I look for, is the heuristics that say, okay, let's make some fundamental assumptions to simplify the objective function and then see if we can cram that into an existing piece of quantum computing hardware. If you have to go to a soup to nuts, high fidelity, data-rich simulation, say of molecular modeling or even an optimization problem, you're not going to get much work done. If you can really think about what are some of the 3 or 4 or 5 most important parameters that you'd like to optimize and convince yourself that those are the ones that matter most, then I think you can start to actually look at the current systems today. And that's how I kind of judge the validity of some of these exercises. Did they do their homework to really say what's important and what's not, and how can I cram that into a quantum computer of today?
Right. So if you can map your problem into the confines of existing NISQ systems, you could even contemplate a production environment sort of a thing, you're saying. Is that correct?
That's exactly right. I mean, look at the history of HPC. 30 years ago, we had by today's standards, very rudimentary HPCs doing stockpile stewardship because it was the best available. So they used heuristics, they used assumptions. Even today, they're still using heuristics and assumptions because the machines still aren't powerful enough. But there was always some reasonable amount of work getting done. And I think that that's kind of we should give quantum the same benefit of the doubt when it comes to that.
I think that's a great point. Now, you mentioned cybersecurity, and besides really good random numbers that quantum systems can do, it kind of leads me to ask you about the segments within quantum science, quantum industry. Quantum communication clearly shows up in cybersecurity, and then quantum sensing has always been there. But then really the nirvana is quantum computing. How would you characterize those segments?
I always have trouble with the cybersecurity use case when
Yeah.
we do these studies, because I think people are still concerned, or at least well aware of the whole post-quantum encryption scheme, fears the experts that make their coin saying save now, decrypt later, which in some sense can be, I think, a little bit of a scare tactic to generate some enthusiasm today for a threat that may not exist for a while. But I think the secure communications aspect of all this is a pretty compelling one. And I think the sensor one, quantum sensors, in my mind, are probably the nearest term quantum application that's going to have some pretty significant use cases and is going to be a pretty big market in the near term. I'm interested and talked a little bit about this, I think, at ISC, the idea that quantum communications actually has three different levels to it, if you will. The first one being the one everyone kind of understands, which is secure communications at distance. Can you do video over a satellite and be convinced no one's listening to you? And that kind of internet-based quantum computing, the progress there is interesting and compelling, but it's something that I think is down the road a little bit. The one that concerns me most from looking at the future potential is quantum communications at the computing level. No one is going out and they're building a 40 million core processor for classical. I hope that we don't have to wait for a million qubit chip in the future. I hope that we can scale. And I hope that we can scale through the same techniques of multiprocessors in QPUs as we do in CPUs or GPUs. So someone's going to have to start to really think about quantum computing network at the computer level. How can I have a quantum computing backplane or a quantum computing router that allows me to distribute the necessary information while staying in the quantum realm? Because if I have to collapse down to classical to do networking, I lose so much functionality. So the scaling issue, in some sense, is really hinging on the ability to develop local, and we could call it quantum lands if you want, but that's really the next great area for research in quantum computing architecture, not quantum processing architectures. And the third one, which I think is really interesting and it ties back to sensors, are quantum networks of quantum sensors. It's really nice if you have a network of quantum sensors to do some interesting work for you, but if you have to have those sensors communicate or operate in a collective way by only being able to transmit data back and forth over a classical network, again, you're going to lose some really spectacular functional capabilities. So the idea of having quantum sensors be able to communicate across a quantum network offers up a whole host of new precision and accuracy and use cases. So to me, the quantum computing space is rich with different opportunities at different levels. It's not just about a secure internet.
That's brilliant. Really excellent points there. Actually, while we're on cybersecurity, I kind of call it the unquantum market, because you really are afraid of quantum computers rather than using them, at least at the moment. You're not using them to encrypt. You're worried that they might decrypt. And that's really an interesting aspect of it, although the random numbers are really important. We never talked about Intel and their silicon spin chip that they put out. What is your view on that? And obviously, I like it because they're using their strengths to kind of approach a completely different market segment. The chip technology right now already has to deal with relativistic quantum effects at the nanometer level. What do you think about that? Is that looking promising to you?
Well, and I knew you were going to ask this question today, so I've been rehearsing an answer all day, and let's have a good one.
Good.
And so let me just tell you what my concern was. When the presentation started, they had an analyst presentation last week where we could sit in and kind of get the early scoop before it was made public. The first couple slides talked about the gap between the invention of the first transistor and when the Intel 4004 came out, and how many decades it took to get from point A to point B. And so we got a really interesting history lesson about how slow the classical world unfolded. And then we kind of made this leap towards, okay, now we're going to talk about quantum. And my takeaway from that first part was, what is the driver to basically so clearly stake out the idea that while there's some fascinating work going on, and I agree with you, I love the idea of building quantum capability on existing CMOS technology and Intel being able to take advantage of its world-class capabilities in lithography and chip making. But I just didn't understand why the emphasis was, we're doing this, we have some interesting ideas, but like we said, it took 4 decades to get from transistors to the 404. What's the takeaway from all that? So I would like to see perhaps a little more, lack of a better term, enthusiasm, because I think Intel has so much to offer. And I just hope that they don't buy into the fact that this is a 20 or 30-year research project, that they have something that they can bring to the table today. I hope they make that 12-qubit chip available to as many research organizations as possible to gain insights, to gather some understanding, and to understand, hey, maybe there are some shortcuts here that you can innovate your way into to shrink that time frame from 30 to 40 years to something a little more exciting than what I saw in that presentation. How was that? Did I insult anybody?
I think that's really valid. And my view is that organizations that focus on HPC, focus on advanced technology, and deliver along those lines do better and they thrive. Now, I hope that Intel is doing this to make sure that they don't promise something that they can't deliver, because that is also a valid thing.
I mean, to me, the opportunity here, and this is always a good thing about the quantum computing sector, as the ecosystem matures, we see more specialization. We see the ability for a different slice of the ecosystem to drill down and optimize something without having to reinvent the wheel. And so to me, anything that says, okay, we've now got yet another slice. We have a major chip vendor interested in supplying quantum components. So now I can think about, okay, are there going to be quantum server makers out there? Is there another, what part of the overall ecosystem does this slice engender? How much does it help accelerate the process by allowing for more specialization? We don't have, the classical world got away from the large vertically integrated companies that built chips so they could sell servers. That business model really didn't work for long once the sector started to mature. So I'm looking at that model to say anything that helps coalesce the stack into making it easier for organizations to really specialize and optimize within a narrow focus. Not that building QPUs is narrow, but now I can go to Intel for QPUs. I can go to an organization like Quantum Machines that builds instrumentation. I can hook up with perhaps a server supplier to integrate that into their IT shop. And then I can either go cloud or go through an orchestration company, like I said earlier, say StrangeWorks, to build a product offering. And so that means I don't have to do it all. I don't have to boil the ocean just to get my quantum vision realized.
The supply chain is forming.
Exactly.
Bob, we talked about cybersecurity, which makes me think of national security implications of quantum. Do you have views, insights on where the U.S. stands as far as we know vis-a-vis China? Because the national security implications of quantum could be very significant.
I think I'm on pretty safe ground if I say the overall emphasis of the U.S. government policy in quantum is to create a competitive domestic commercial capability that the U.S. government can draw on for the technology they need. And that's really been the effective working model, because government programs to develop technology that are in competition with the commercial sector invariably seem to cost more and just progress at a slower rate. Now, for things like stealth or hypersonics, or my personal favorite, nuclear-powered subs, where there's no commercial counterpart, the government must hold sway. But the key here for the U.S. government is the ability to draw on a vibrant domestic commercial sector to fulfill their specific needs for national security agenda requirements. China is going, in some sense, the other way. They have a much greater commitment towards creating an infrastructure that can serve their military and national security agenda. They are not as active in promoting a commercial sector, which means that if government policy there correctly takes the right research direction, correctly defines the scope and implementation of a vibrant quantum computing capability, then all power to them. That is not as risk tolerant as a aggressive, innovative commercial sector. And while the chances for success are good there, there's not a lot of cases where centralized government planning, in the emergence of a new technology that has a commercial counterpart, where that government program has really succeeded for very long. So the national security agenda issue here is really a competition between centralized government planning in China and a much more vibrant, innovative, risk-taking commercial sector here in the United States.
And, it's interesting because with the U.S. approach, as you say, a vibrant commercial sector, that also necessarily means it's all wide open. I mean, anybody in the world can access, say, IBM Quantum in the cloud. So we're open.
Well, the Department of Commerce, Bureau of Export Control may have different thoughts going forward, where I think we're going to start to see a certain amount of chilling in the openness of the sector because of the national security overlays. We've already seen commitments to domestic supply chain assurance and such. So the trend is really more away from the openness. I think Tom Friedman and the world is flat. Most of us kind of understand that politically that may not be the proper solution. Maybe we gave away too much in the last 20 years because the world certainly isn't flat. It's clumpy, and I think it's going to grow increasingly clumpy over time. And whether that hurts the sector from a global perspective, or at least from a technological progress perspective, is something that remains to be seen, but it just does need to be managed thoughtfully, because access to the materials, and in fact, I think more importantly, access to a global base of quantum computing experts is necessary to keep the trajectory of the technology going forward. If US companies can't get access to the best quantum researchers in the world, by definition, they suffer, because it just means that you're going to duplicate effort. You may go down the wrong path that someone else has already gone down. It introduces inefficiencies. So while the quantum supply chain from a material standpoint, I think is worrisome, the issue of controlling expertise is one that I hope that we can look at a bit more sophisticated in the coming years.
Yeah.
Really well said.
Now, I guess my last question would be, we hear about different quantum approaches or techniques, or I don't know if the word is architectures, but we see, silicon spin neutral, atom, and then diamond. It seems like such a decentralized approach to the development of this technology. I assume it's way too early to call a winner or even place a bet on the winning approach. Is that the case?
I think that looking at it at that degree of precision is not really a fruitful exercise. I think that the organization or organizations that develop the compelling use cases, remember my earlier comment about people aren't going to buy super chips, they're going to buy applications that need super chips. I think that if you have a compelling use case, the typical user is simply not going to be too concerned about the particular modality it requires to get to that application. I think as long as it can be easily integrated into their existing classical IT infrastructure and it's got demonstrated performance gains, I don't think the end user is going to care too much about that. And so that means if you want to be a successful quantum computing company, you should moderate how much technical information you get away with versus how much discussion you can have with an end user who's interested in results. And the example I'll give you is IBM just introduced kind of the next generation architecture for basically small node, process node chips. We're moving from something called FinFET to gate-all-around architecture. I'm not going to buy an HPE server based on gate-all-around architecture because I frankly don't know exactly. I mean, we're talking about 150 billion transistors using this technology, but it doesn't translate to a high degree of interest for an end user. And so I use that same model. People don't really want to know too much about the details under the hood if they have enough details about how fast the car goes.
Bob, this has been excellent.
So much fun to talk to you guys. And I will say I had a big sticker over my monitors that said, don't talk too much. So I hope I at least hit a little bit of that mark. But it was great having a discussion with you guys, as always.
As always, pithy and very insightful. And this is such a rapidly developing and so critical piece of technology. I'm delighted that you're focused on it and we can take advantage of your expertise.
Outstanding. Thank you so much for taking the time today.
Thank you, Bob.
Take care.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.